All right, so now we want to get a little more analytical in our discussion of dynamics. So this video covers section 2-1 in the book. That is chapter 2, section 1, and it deals with position, velocity, acceleration, and all of its in Cartesian coordinates. And specifically, we're talking about particle kinematics. So kinematics studies the geometry of motion. So really what we want to be able to do is determine the position, velocity, and acceleration of any particle. And one thing to keep in mind is that these are all vectors. So they all have a magnitude and a direction. So the position of a particle, its velocity, and acceleration all have magnitude and direction, and you have to keep that in mind. We'll talk about speed later, and speed is the magnitude of the velocity. So speed doesn't have a direction, but velocity does. Now we're going to need to deal with time derivatives a lot. The derivative of the position vector is the velocity vector, and the derivative of the velocity vector is the acceleration. So we'll deal with those constantly. So we just want to get the notation right. So if we have some function f, the dt we'll call f dot, and that's the first time derivative. The second time derivative is f double dot. The third time derivative is f triple dot, etc. So let's start with the position vector. So the position vector is provided in some kind of coordinate system. So in this case, we'll have an xy coordinate system with unit vectors I and j in the x and y directions respectively, an origin at point O. And we want to be able to describe the position of a particle at any time. And so what we use is this vector from the origin to the particle, and it's a function of time. So if we know this vector r as a function of time, we'll be able to identify the position of the particle at any time. And if we can do that, and we can take some time derivatives, we'll be able to specify velocity vectors and acceleration vectors just by differentiating the position. So r is our position vector for particle p. If we want to break that into the horizontal and vertical components, x sub p is the x coordinate of the position vector, and y sub p is the y coordinate. So this position vector r can be broken up into the x and y components, x sub p of t multiplied by the unit vector in the x direction plus yp of t multiplied by the unit vector in the j direction. Okay, so x and y are the coordinates of p, or x sub p and y sub p. If we want to know the distance from the origin to the particle at any time, we can just take the magnitude of the position vector, which is the sum of the squares of the individual x and y components. So then we'll talk about trajectories. So the trajectory of a point is the line traced through the space point by point. It's sort of like if the particle leaves a trail as it moves, then that would mark out the trajectory. Okay, so the position vector is a straight line from the origin to point to the particle, but the trajectory is the path it takes to get there. Okay, so if we just know the position vector at a specific time, it doesn't tell us anything about how the particle got there, but the trajectory does. So this dotted path is a trajectory, and if we know what that is, we can kind of trace out in history where the particle has been. Okay. So now we'll talk about displacements and average velocity. So the displacement between two different times is the change in position, right? So if we look at this particle p, at time ti, particle p was here. At time tj, particle p has moved to here. So we have a particle, position vector r of ti that denotes this position, and r of tj, which denotes this position. And the displacement is the change. So it's this delta r here. It's the vector connecting where it was at ti and where it is at tj. Okay, so the displacement just tells you the change from one time to another. It doesn't tell you again how it got there. So if this was our trajectory, the displacement vector is independent of that trajectory. It's just where the um, path or the vector between these two positions. All right, so delta r at for as you know as a function of 2 times delta r of ti and tj is the change in position or the difference between the two vectors, the position vectors. The average velocity over that um, over that time period is the change, the displacement or the change in position or the distance traveled divided by the time, right? And the distance traveled, because we just draw this straight line from these two positions, the distance traveled is delta r. It's just the change in the position, right? So delta r here divided by the time it took to make that change, so tj minus ti. So it's like delta r over delta t. So that's the average velocity. Okay, so the distance between the two positions, p of tj and p of ti, is the magnitude of the displacement vector. Okay, so it's the magnitude of delta r. So the distance traveled during the time interval is the length of the yellow curve, right? So the displacement is just this delta r, but the distance actually traveled has to take into account the trajectory, and it's the length of this curve, which is highlighted in yellow here. Okay, so that's the distinction between displacement and distance traveled. Displacement is just the straight line, it's a change in position from one time to another. And the distance traveled takes into account how you got there, and it takes into account how far you actually traveled. So the velocity of the particle is defined as the limit, as delta t goes to 0, of the average velocity between some time t and some later time t plus delta t. Okay? But if you look at the limit as t goes to 0, then this displacement or this trajectory will be a straight line if delta t is small enough, or can be approximated as such. And so if you work it out, the velocity is just the time derivative of the position, okay, or r dot. I said that before, but now we have derived it, at least in a crude fashion. Okay, so the main thing here is that if you know the position vector is a function of time, you take the time derivative and you get the velocity vector. Remember, velocity is a vector, so it has magnitude and direction. Okay, and so speed, as I said earlier, is the magnitude of the velocity. So speed tells you how fast you're going, but it doesn't tell you the direction. It's always positive. Okay, so speed is a scalar, velocity is a vector. We can relate the velocity to the path. Okay, so suppose in this example there's a street here that's a curved street, and there's a car driving along that curve. Oops. So there's a car driving along that curve, and it has drawn out here 5 positions: P1, P2, P3, P4, P5. These are the positions of the car um, at 5 different times, T1 through T5. If we look at the velocity vector, or the change in position, then if we compare P1 to P5, it's this blue vector here. Okay, so the change in the position vector from time 1 to time 5 is this blue vector. From time 1 to time 4, it's this one. From 1 to 3, it's this one. From 1 to 2, it's this one. And if you just think about the limit as the change in time goes to 0, you'll notice that the red line represents the tangent to the curve, and the change in position will be along that tangent. So the moral of this story is that the velocity vector, which is proportional to that change in position, is always tangent to the path. So if you're going around a curve at any point, the velocity vector is tangent to that trajectory. And that's an important thing to remember as we go through all this. So once we work out velocity, then we're interested in the acceleration. Acceleration is the time rate of change of velocity. Since the velocity is a time rate of change of position, then the acceleration is the second derivative of the position. So if we know the position vector is a function of time, one derivative gives us velocity vector, two derivatives gives us acceleration vector. So we can write this as v dot or r double dot. Don't forget acceleration is a vector. And the thing to note here is the acceleration is generally not tangent to the path. So velocity always is tangent. Acceleration is generally not. It can be, but it isn't necessarily. So let's look at a simple example. So we have an XY coordinate system here and some particle P which is traveling on the trajectory denoted by this dotted line. So this is the path of particle P. And at points A, B, and C, the velocity vectors are noted. So right here, the velocity is tangent to the path, and so it's in this direction. At point P, it's tangent, so now it's in this direction. At point C, it's tangent, it's this direction. Somewhere over here, the velocity vector would be perfectly vertical because the tangent is vertical. All right. But if we look here at, say, time, the velocity at time t will be here, and then as we go around the curve, the velocity at a slightly later time will be tangent here, and you can see that the velocity vector shifted from this direction to this direction. So the acceleration is related to the change in velocity, and therefore it's more like in this direction, okay? Because we're moving from going in this direction to this direction, so the change in velocity is more like in this direction. So the acceleration is this way, not tangent to the path, and that just reinforces this comment I made earlier that the acceleration is not tangent. All right, so we can work out velocity, speed, and acceleration in Cartesian coordinates. All right, so if we know x of t and y of t, the x and y coordinates of the position vector, then the velocity is just x dot times the unit vector in the I direction plus y dot times the unit vector in the j direction. Quite often we'll call x dot vx, so it's the x component of the velocity, and the y dot is vy, and that's the y component of the velocity. So the velocity vector can be written as vx times the unit vector in the x direction plus vy times the unit vector in the y direction. So the speed is just the magnitude of this vector, it's just the square root of the sum of the squares of the velocity components in the x and y direction. And we can write those as x dot and y dot, so it's the square root of x dot squared plus y dot squared. The acceleration is x double dot times the unit vector in the x direction plus y double dot times the unit vector in the y direction, which is vx dot times I hat plus vy dot times j hat, or ax times I hat plus ay times j hat. All right, so it's the acceleration in the x direction times unit vector in the x direction plus acceleration in the y direction times unit vector in the y direction. So let's do one quick example to kind of walk through some of this stuff. So the idea here is we have a couple of ships in the ocean, say. There's ship A, which is at this location and then oriented with the x-axis in the A coordinate system perpendicular to the ship and the y direction along the ship axis. And then there's a ship B with its x coordinate along the axis of the ship and the y coordinate perpendicular to the ship. So we have a ship A and ship B. Each has their own coordinate system, and we can look at position and velocity and acceleration in each of these coordinate systems. So the idea here is that ship A has launched some projectile P in the x direction, in its own x direction, so in the xa direction. So P is flying along this. So the position vector for P in the A coordinate system is given to us as 2.35 t cubed times the unit vector in the xa direction. Okay, and the units are meters. So relative to the B coordinate system, this thing's flying at this angle, and in the B coordinate system, that position vector has an x component and a y component, right? So in the A coordinate system, it only has an x component, but in the B coordinate system, it has an x and a y. And so the x and y coordinates in the B coordinate system are given here: 225 plus 2.13 t cubed times the unit vector in the xb direction, and then 225 plus 0.993 t cubed times the unit vector in the yb direction. Okay, and t is in seconds, and the result here gives you distance or position in meters. So the three questions we're trying to answer is the path of P as viewed by frame A or frame B, the velocity and the speed, and then the acceleration and its orientation in each of the frames. So we have the position, P is a function of time in both coordinate systems, and we can just take some derivatives to solve this, okay? So first, we want to know the path of P. So in the A coordinate system, the path is just along the XA direction. It's pretty straightforward, okay? So that's, I say down here, in frame A, YPA is 0. That is the position vector in the YA direction is 0. And so we need to calculate the path. The path is just along the XA direction. In the other, what we know XP set B, right? We know the x coordinate in the B frame as a function of time and the y coordinate in the B frame as a function of time. To get the path, you just eliminate the time and we'll get x as a function of y, and that'll be, as we'll see, a straight line in the B coordinate system. All right, so we just solve one of these for t, substitute in the other one, we eliminate t, and we have y as a function of x. So we do that. We solve the first for t. It gives us this: t cubed is xpb minus 225 over 2.13. We stick that in over here for t, and we get ypb is, if we work out some of the math, 120 plus 0.466 xpb. So that's just a straight line in the B coordinate system. So the position vector of that projectile in the B coordinate system is a straight line with a slope and an intercept. So if you're sitting on boat B and you see this thing flying off in this direction, it's flying in a straight line, but it's not along either the XB or YB axes. It's going at an angle, and that's why it's this straight line given by this. And that's the path. So to get the path of a particle, when you know the XY coordinates, you just eliminate time, and it gives you a function of X and Y. All right, so if you're sitting on B, then you see the projectile moving in this angle, and that's the path. All right. So part B, we want to know the velocity and speed. So if you're sitting on boat A, then the velocity is just r dot, and r from boat A just has one coordinate system. It's going in the XA direction. So you differentiate the position vector, and you get 7.05 t squared times the unit vector in the XA direction, and the units are meters per second. In B, we have both an x and y coordinate, so the velocity of the particle P in the B system is the time derivative of the position vector in the B system, and there's an x and y coordinate. So you get you just take the time derivative term by term, you get 6.39 t squared times the unit vector in the xb direction plus 2.98 t squared times unit vector in the yb direction. To get the speed, it's just the magnitude of these. Since this only has an x coordinate, then it's pretty trivial to find the magnitude. It's just 7.05 t squared. So the velocity is increasing like t squared, so it's ramping up pretty quickly, and the units are meters per second. In the B system, you have two components, so you have to take the square root of the sum of the squares. So we do that, and we end up with the same thing, 7.05 t squared. And that's good, because since boats A and B are stationary, they're not moving, then they should observe the same velocity from that particle. And so we get the same velocity no matter which coordinate system we're working in, and for this kind of problem, that's a good check. As long as the coordinate systems aren't moving, we should see the same velocity from each. And finally, we want to work out the acceleration. Again, we're just taking time derivatives. So the acceleration in the a coordinate system is just the time derivative of the velocity in the a coordinate system. And again, there's just one component, so we just take the time derivative, and we get 14.1 t times the unit vector in the a direction, and the units are meters per second squared. In the b coordinate system, and this should say as seen by b, the acceleration of p relative to b is just the time derivative of the velocity vector, and that has two components. You differentiate term by term, you get 12.8 t plus 5.96 times the unit vector in the I direction plus 5.96 t times unit vector in the y direction for b. Okay, same units. We just have two components here because the thing is accelerating off at an angle. All right, now if you want to get the orientation of the acceleration and the velocity for that matter, you can look at the relative components, right? So, for example, if we want to know the orientation of the velocity vector, then the tangent of that orientation is just the ratio of the component. So if we look back here, see if I can find a good picture. So if this is what the path looks like, then we'll have acceleration vectors or velocity vectors along that path. Let's say if we just focus on velocity, the velocity has to be tangent to the path, so the velocity will be along this direction. So if we take the ratio of the y component of the velocity to the x component of the velocity, that'll tell us the tangent of this angle. If we take the arctangent, then it'll get us the angle, right? So you can find the trajectory, the orientation of the trajectory by taking the ratio of the x and y, or the y and x components. So that's what we're doing here. We're taking Vy over Vx, and then we're taking the inverse tangent to get the orientation angle. Y is 2.98 t squared. Vx is 6.39 t squared. The t squareds cancel, and so we get the tangent inverse of 2.98 over 6.39. It comes out to 25 degrees, and it's independent of time. So the orientation is at 25 degrees from the horizontal, and that's its orientation. For the acceleration, we just take the ratio of the components of the acceleration vector, ay and ax. Again, the t's cancel, and in this case, the acceleration is tangent because it's a straight line path, and so we also get 25 degrees for the acceleration. So we know the magnitude of the acceleration, the magnitude of the velocity, we know the orientation. We pretty much know everything we need to know about that particle in the two coordinate systems A and B. All right, so that's it. Hopefully that'll help you work out some of the homework problems.